Hello YouTube viewers, welcome to my channel Science to Technology. In today's show, Science Thursday, we're gonna talk about light-emitting diodes. So let's dive right into it. Now, first thing you have to understand, we are talking about a semiconductor light source. Basically, what's LED made of? Semiconductor. So as our semiconductor technology that is driving our computer industry improved, this also improved alongside it because of better chemistry management, because of better manufacturing equipments, all those jazz. Basically, these are parallel industry. Better understanding of silicon allows us to make better semiconductor, which allows us to make better LEDs. So fundamentally, these two are industry-wise, they are linked. So what we are talking about here is electroluminescent. Now, you may be thinking this simply means take electricity, create light. Now, that's absolutely true, but you may think that, hey, what about incandescent light bulb? It also does the same thing. It takes electricity, gives you light. So what's the difference? Well, that's not happening. That's not what happening inside a bulb. What's happening in a fluorescent bulb? You take electrical energy, you heat it up. So you have electricity, you have heat, then you have thermal luminance. Basically, you heat this puppy up to as hot as possible, and then it starts to radiate photons. Trying to cool itself down. So fundamentally, you are talking about almost a thermal system. That's why the color temperature is always measured in Kelvin. Basically, how hot it has to go, get in order to how much color. Basically, bluish requires it to get even hotter. So that's why halogen and all that jazz, they go even higher temperature. So fundamentally, you take electricity, you make heat. Heat gives you light. Here is like you take electricity, you get light. Now, one of the most amazing aspect of this technology is that this puppy is solid state. I do not have to tell you that bulbs are fragile. You drop them, bye-bye. Now, CFLs, while they are a bit more rigid, bit more well-built, but they are still drop them, bye-bye. So LEDs, on the other hand, good luck trying to break them. Like, you have to try to break them. Like, these things are so robustly built. I have literally seen during some festivals going around in my house, people had the like old halogens, like they were careful with this, like, don't just drop it. With modern LEDs, they're like, yeah, just check it there, who cares, it's like, ain't got time for this. So that's the reality of it. This is a solid state. There is no glass tube, there is nothing fragile. Inherently, this is a solid system. What does that mean? That simply means unless you are trying to break it, you will not able to break it. And if it's well built, it's designed to withstand some abuse, good luck trying to break it. So that's amazing for lot of use case scenario, specifically like cars and all the jazz. Like, why? Cars, they go through a lot of vibration, so filament inherently over time gets damaged. But like truck drivers have a long horrifying history, and many truck drivers have switched to LEDs because of this reason. So what's the logic behind it? What's the core principle? What makes it glow? So we are talking about a PN type junction. What does that mean? That simply means this puppy is a diode. And what you're gonna do is basically take a system that has N type. What does that mean? That simply means this puppy, the silicon or whatever material you are choosing, there are many types of semiconductor. Whatever semiconductor you are choosing, you are doping it, and you are doping this puppy in a such a way that it has overflow of electrons. Basically, it's an N type. Then on the other side, you're gonna have basically P type, which has basically holes. Basically, electron can easily come here. Now you're gonna connect them. Now you may think this sounds exactly like solar panel. Well, it is a solar panel, fundamentally speaking. Only how you are fine tuning is that's the difference. So you can, in principle and in reality, take a solar panel, make it glow, and you can take a LED, make a solar panel out of it. I have provided the video down below, but be mindful, those are a very inefficient use of it, waste of energy, because again, those are not fine tuned for it. So inherently the same thing is happening. Now you have a junction, you have overflow of electron and lack of electron in one way, and then you feed electricity right way. Now electron comes here, N type, it gets overexcited, already has basically positively a lot of electrons. Now you are forcing more into it. So what happens is like electrons jumps this band gap. It's like, nope, I need to calm down. Basically, things like to return to equilibrium. So it's like, okay, P type is the best place to go. Now they want to go there. Now think of it this way, you dumped 100 of energy in per electron, you dumped 100 into it. It's like, okay, 100, I have 100 of energy. Now whole is like, no, I will not accept 100, I will only accept 90. So what the electron to do? So electron does what every electron does. It's like, okay, I'm gonna emit one photon for this. So electron basically dumps its excess energy in photon form, and that's why you get direct electricity, direct photon production directly. There is no hoo-ha happening. It's exactly like solar panel, like photon, electron movement, photon. That's it, as simple as that. So So basically, the more power you feed into this, the more the electron is like, trying to rush to the p junctions, and the more they have to rush, the more they have to dump their excess energy into photons, and brighter your LED glows. Now, one thing you have to understand here: all LEDs are inherently monochromatic. What does that mean? That's simply based on the mixture that you are using, basically N type and P type, and what kind of semiconductor you are utilizing. You're gonna get a single color. You're gonna get red, you're gonna get green, you're gonna get yellow, you're gonna get blue, but you're never gonna get white light. So you're like, wait a minute, how the heck we have white LEDs? Because like I have 100-watt white LEDs here. How the heck we have that? Well, we don't technically. What we have is blue LED. Now blue LED creates a lot of high energy photons, high energy being blue spectrum. Now you can send that puppy to a specific layer known as phosphorus. Now depending on the composition, depending on the mixture, depending on the thickness, application, and all the jazz, you can create in a fine tune in such a way that basically, think of this way: 400 volts went in and 200 volts, two channel came out. So you can have like one blue photon goes in and one green and one red photon come out on the other end. Now you're like, what does that mean? That was basically like how we used to convert, basically there are many types of lamps that utilize ultraviolet production, and then utilizing phosphorus layer creates visible light. Same thing is happening here. So we have very efficient blue LEDs, awesome. All LEDs are monochromatic. That goes to the phosphorus layer, and phosphorus layer converts blue light into basically other colors. Now because the blue light is so intense, some basically phosphorus is not going to convert. Let's say 100-watt was created here, it's not going to convert 100 into that. You will never make it that thick. You're going to make it thick enough where it's like, based on color balancing, you can be like, hey, just convert, let's say 50 watts of energy of blue light into other spectrum, so it creates an even system. Or you may be like, hey, it's still too blue, like the LEDs are cool white. You may be like, okay, let's make the phosphorus more thicker, so it converts more of the blue into basically red and green. So that's how we get white light. And that's why even though your old VCR remotes had LEDs into that, we still never utilized them into lights. While the LEDs, we made them very early on, we made them efficient very early on, but figuring this part out, white LEDs, that took time. So figure out that phosphorus mixture and figure out how to mass produce them cheaply enough took time, and we are still doing a lot of research into that department itself. Now, one thing you have to understand, this is a semiconductor technology, so driving it is not simple. Like same thing I talked about, like surge protector video of mine is like, our old equipments, they were kind of robust against electrical spikes. However, semiconductors, they do not like spikes at all. So this puppy is a semiconductor system. So how the heck are you supposed to drive it? First thing you have to understand, it always works on DC because it's a directly diode, so to say, and it's polarity sensitive. So you have to provide it electricity properly. Best case scenario, it's not gonna glow if you wrongly plug it. Worst case scenario is gonna go boom. So that's one very critical thing you have to understand. Now, one thing, the biggest limitation of LEDs itself is that inherently it does not have the ability to limit current. Like a resistor can limit current. It's like, hey, I'm only designed to let this amount of current, ampere, go through me, and it's like, unless you are doing something extreme with it, it's like I can manage that. LEDs, on the other hand, they do not have that kind of lock to electricity. They are like, oh, you want to send more than 3 amps, like it's designed for 3 amps. It's like, hey, you want to send more than 3 amps, send it, I can accept it. You want to send more, okay, I can keep accepting. And that's why LEDs go boom. So fundamentally, whatever driver you are designing, the first function and the primary function it must do is limit the current. That's why even a very basic LED flashlights, even a very cheap one, will still have a resistor acting as a current limiting resistor. That's the one thing you must understand. As long as you can limit the current going into LEDs is gonna inherently live for basically as long as the universe lives. And that's too far out, but you get the point. It's gonna live for a very long time. So that's the main thing. If you want your LEDs to last long, you must limit the current. Then we come to how the heck you want to dim it. For many applications, you want to dim it. So in those sorts of scenario, you have two primary modes of operation. Operation number one, you do pulse width modulation. You basically blink it as quickly as possible, higher than 50 hertz. Like I'm talking like 250 hertz or like 500 hertz or sometimes 5000 hertz. Video lights sometimes do that. If they really have to achieve very low flicker rate for video cameras, they will do that, like 5000 hertz or like megahertz, kilohertz kind of switching. But it does introduce flicker, and human eyes are susceptible to flicker if you have a lot of motion. Basically, if you're doing like this and we have flicker, you're gonna instantly recognize that, and it's gonna drain you. It's gonna feel bad basically for you. So many times workshop do not introduce lights that have flicker. They will try to get lights that inherently do not have flicker. So how the heck you're gonna achieve dimming without flickering is control the voltage. Ampere is locked unit. Basically 3 amp LED means 3 amp LED. You cannot tamper with that, but voltage is free. You can easily tone down the voltage. It's like, hey, let's say it starts to glow at 3.2 volts. You can be like, hey, what about 3 volts? What about 2.5 volts? What about 2.4 volts? Depending on LED's basically semiconductor type, it could go very low or it could go very high. So that gives you brightness color without flicker. Now this is the primary method of making a video LED light. Be very mindful of that. Do not do PWM on a video system. It's gonna introduce very weird flicker, specifically if you have something moving. Then heat sink for temperature control. Now this may sound odd. It's like, hey, we are talking about bulbs which has to get hot in order to produce light. Why the heck LED is getting hot, even though it has a band gap where all we are doing is releasing basically energy in terms of photons. While we are releasing a lot of energy in terms of photons, we still have a lot of basically infrared photons also, and sometimes we have a lot of basically inherent friction, basically resistance of the material itself, and that is creating a lot of heat. And because the older LED systems, we had each individual LED spread out far. Now because of the world that we have inherited, now we have COPS, what we call chip on board system. So those are very densely packed. So you are talking about, let's say, a waste heat of 10 watts on a 100-watt LED array that was like this big. You are talking about 10-watt heat in this much area. That's a very mild temperature. Now you take that heat and you put us in like a small area. You're talking about a soldering iron. So you have to cool that, because heat will make things more resistive. That will force more current to flow through. That will increase the temperature even more insane, and LED will go through what we call burnout. Basically, it's gonna self-destruct because of not having current limiting capacity. So that's why we must have heat sink to control the temperature. Now biggest limitation on lifespan on any LED, even the cheaply built one, is like how good the driver is. Now if you're talking about something very expensive, like say for example research grade LEDs, cinema grade LEDs, or like very high color rendering index LEDs, basically you have basic LEDs that is around 70%, you have 80%, you have 90%. Now the cost is ludicrously high, 98%. That's idiotically high. And if you want to make sure that LED is taken care of, you will have the best heat sink possible. You're gonna have best flexure possible, but be mindful, you're gonna design the driver in such a way that in any case, if any fault condition is created because of mains ripple in the mains voltage or things of that nature, is gonna go boom rather than the LED. So if you are talking about some very expensive equipment, you could literally have, hey, we had this LED fixture for like, let's say 20 years, and we had changed the driver for like 2 times. You have changed the driver. So you could easily have a scenario where LED outlasts the driver. So that does happen. And one LED, if done correctly, if designed properly, and if you have good electricity, mains electricity, because if mains is really bad, it can literally jump through whatever protection you have. Heck, if lightning falls on your mains electricity, this is not going to do much. So depending on the condition, depending on the limitations, you can literally have a LED that can outlast the driver systems. Now we are living in a world of COP at this point, in chip on board. Now there is a bigger brother of COP, that is DOB. Now DOB is basically driver on board. So somebody came up with the idea, is like have as many basically diodes as possible in a small area. Awesome. It makes high brightness application possible, like car headlights. Awesome. It does require heat sink, but we can manage that. Okay, everything is awesome. What is the next big thing? Put the goddamn driver itself. Now what we are doing nowadays is basically each LED has a voltage drop. So let's say 3-volt voltage drop. What if you have a lot of string of it, like a lot of 70 LEDs? In those sort of scenario, you can have a scenario where the voltage drop is around mains voltage, as in 100 volt in a 100-volt system, or 200 volt in case of other voltage system. So you could literally have LEDs that are requiring, like, even if you have DC voltage, you have to feed it 200 volts of electrical energy potential to like get it to light up. That's what we are doing. That's what these things are. That's why they are so simple, so cheap. All they are doing is directly running on mains. Now they do have bridge rectification, because LEDs are polar sensitive. They do have bridge rectification, but they do not do the buffer the system. Basically AC we know like this. So everything is awesome. Now DC on a paper book, so you see it's a dash line, but if you take basically output from a bridge rectifier, you're gonna get, it's never gonna go in negative system, but it's gonna be like this, because you are not buffering it through a capacitor, you're not limiting it through an inductor, you're not doing anything to it. It's inherently unstable. Now the what we call unbuffered DC, so you can feed that unbuffered DC directly into these LEDs, and voila, you directly have a what we call driverless system. Now everything is awesome. It does work, and it's very cheap to manufacture. So what benefit of this is, it's simple, it's cheap, and it's very powerful. Like you are talking about like around paying for $1 for 100 watt of LED power. That's super cheap. super duper idiotically cheap. Now there is a consequence of this, because it's directly going through unbuffered DC. The DC inherently has off time, so it has idiotically high flicker rate. So this puppy flickers a lot. Specifically, if you want to use that for video lighting, try to be at lower frame rate, around 30 fps. So if you are higher frame rate and a higher shutter speed, you're gonna notice it, specifically if I'm moving a lot. Then it also has low efficiency, because there is no buffering, because there is no fine tuning. You have driver ICs that are like just gonna dump the excess energy. Basically they try to let's say if you take 200 volt AC system, you make it into DC, your DC voltage could be higher. You could be like talking about 300 volt. So you will design it in such a way that LEDs light up at 250, but what happens when your DC goes higher than that? It's gonna dump that energy. So these things require a lot of cooling. Even though they are running directly, they do not have to convert, basically they do not need a transformer or switch mode power supply. They still get hot. And one of the most common complaint, like people buy these things and they're like, because it's a large plate, and you will think, hey, it's spread out, it's not supposed to heat up. Because of the inherent inefficiency, it heats up. So even though you are utilizing these puppies, please make sure you have a good heat sink to these things. Only then this puppy will last, otherwise they will burn out. So that is the world of DOP. Now what we're gonna expect in the future at this point in time? Right now, what most companies are working on, let's say Cree, Billy, Philips, or whatever company you're talking about, they're working on better white light production. At this point in time, that is the biggest limitation. When we had incandescent light bulb, you can take incandescent light bulb, you can send that light spectrum through a prism, and it's gonna be awesome. It's gonna be smooth, there is no gonna be spike, it's gonna be awesome. Basically, we want something like a solar spectrum. Why? Everything we see, everything we perceive, our brain, our eyes, our whole DNA is fine-tuned around solar spectrum, because we live under the sun. So everything, basically colors of the object, if lit by this spectrum, looks awesome. Anything other than that core spectrum looks odd. That's why many people do not like CFL light bulbs, because it makes skin look very quote-unquote sickly or pale, simply because the spectrum is not aligned properly. Now right now, if you buy a very cheap LED, it's gonna have like a white LED I'm talking about, it's gonna have a blue spike, and it's gonna try to, but right now you can see that curve is not matching to this. We have to make this match, otherwise inherently it's unnatural. So fundamentally, a lot of companies are working on figuring that out, and there is one company that trying to do something amazing, or I do not know whether it's going to succeed or not, but they are trying to do something interesting. It's like they have pulper LEDs, and they have three phosphorus systems. So they have basically they are taking purple and making into blue, purple to green, purple to red, and because of they are fine tuning the mixture, they can create a spectrum that is almost gentle, and like it's like rather than having the spike, it has a completely smooth curve, like curve that is matching solar spectrum. So like color rendering index, while it's a good metric, it's not precise enough. Scientifically, you have to go through the spectrum system. So they are making very good LEDs at this point in time, and that's what every company is trying to focus on, making sure the color rendering is absolute, trying to make sure the spectrum matches. Then another aspect is, while very super expensive LEDs, they are very good even in a cob array. The cheap ones, the biggest problem they have is they do not have basically good manufacturing tolerance. So basically one diode could be triggered at 3 volts, another could be at 3.2 volts, another can be 2.8 volt. What does that mean? That simply means because you are not controlling each LED individually, you're talking about a string of LED, you can provide best control possible. You can provide like absolute voltage, absolute current, everything awesomely done, but the string itself could burn up simply because there was one goddamn LED that was like, nope, my resistance is too low or my resistance is too high. They are not properly matched. So that's why cheap LED arrays do not last very long. Inherently, that's the inherent inbuilt limitation, quote unquote. So that's one thing that you have to figure out. Otherwise, it is figured out. It's just like you have to be like very rich to afford it. So that's one thing that people are trying to figure out. And what universities, PhD universities are doing, they're trying to figure out how to reduce the heat load, basically the energy, the resistance. Basically they're trying to reduce the effect of resistance and trying to improve the efficiency of electron jump. Basically, rather than creating heat, just create more photons. We are trying to do that, and we are getting better at it. And there are some systems that are very efficient. Basically there are some systems that rather than creating heat, it's like running at more than 100% efficiency. I'm like, what the hell? Then turns out it's acting like a refrigeration system. So there are some amazing things that are being done in the lab. But right now, the most interesting thing that I can easily see in next 10 years is like having a spectrum where we do not think about color anymore, because it's absolute solar spectrum. So this was my presentation on LED. I hope you liked it, learned from it. In that case, please click the like button, share it amongst a friend. That will help me a lot. If you didn't like it, didn't enjoy it, I urge you to press dislike, press it twice to show me extra disappointment. Please leave a comment because I try to reply to all of them. Subscribe, press the bell icon if you're free, and as always, thanks for watching.